Hi, everyone. How's it going? I'm good too. So today, I don't think we're going to get through with all this material, but we'll see how far we get. And I think last time we ended with this discussion. The last class reporting was posted this morning. I did post it this morning. Do you not see it on Quarkus? Let me. It should be. I always delete the one from last week. And the upper link, the first one of these two links to YouTube is always the one from Wednesday, and the second one is the one from Thursday. So this should be, yeah, this is lecture 5. So it's working. Last week, Wednesdays was taken down because in this course, we'll only make available the lectures for 1 week so that it incentivizes you to watch the lectures within the week that it happened. Otherwise, it could happen that some of you will watch them like a series, like a binging a series at the end of the semester. And we want to encourage you to watch it right away when it happened. Any questions before we start? You're welcome to already start thinking about this discussion. So we'll start with this in a minute. Actually, I wasn't sure if I should give you this link, but when I'm slow uploading the notes to Quarkus, you could actually, I don't know if you're familiar with GitHub, but I'm actually storing my the lectures on GitHub. So if you go to github.com /researchnext, and then / I think it's Matt. I don't know why I'm writing at an angle. It should be MAT224. Then you can find the lecture notes there as well, but they might be under construction up until the point that the lecture happens. So if you want to be sure that you have the latest version, this is a way that you can just download the slides directly. Let me just check that this is the correct link. Yeah, so this is a quick access. This is where I will have the every version of the notes, and then only the final version I'll upload. So if you're curious to see and maybe read them earlier than they're available on Quarkus, you can go to this link. But be aware that they are under construction and maybe a lot of mistakes in the beginning, and I'm only finalizing them the day of the lecture sometimes. Okay, so I think we can continue with the lecture or start for today. So this is where we left off today, and let me just say in a few sentences what happened yesterday. So we were able to show a very important corollary, namely we were able to show that every vector space which has some finiteness condition actually has a basis. So this means in the future, whenever we are working with a vector space, we're able to assume that there's a basis and then work with the basis. And the basis is very helpful in many ways. So this is the big result from yesterday. And to practice this, I want to start with a discussion to try to build a basis from two given polynomials. So in this discussion, you're given two polynomials, p of x equals 1 plus x, and q of x equals to 1 plus x squared. And now the objective of this discussion is to find a third vector r of x, such that the family of p, q, and r is a basis for p2r. I'll give you 2 minutes or 2.5 to think about this, and then we'll discuss this together. Please don't post anything in the chat while the discussion is going on, because that would spoil the answer, and I want to give everyone a chance to think about this. If you have questions, though, you're welcome to ask them in the chat. All right, who has an idea? And if you can, maybe try to argue with a theorem that we had before. So maybe try to use the theorem that we just had, because this discussion is there for a reason. It's placed directly after the theorem for a reason. But if you have another idea, just yes, Oliver.
So I think the third vector x minus 1 will be a when put in with PQR as a basis for because it can be it's independent from the two, meaning that there's not a linear combination that could be made from P and Q to get R. And I didn't think of a theorem, but uh, um, I guess we can use the enlarge theorem and say um, that we can enlarge it while until uh, I'm not actually sure, but maybe we could use that. I'm not, but
Yeah, that's absolutely correct. I mean, this is a good guess, and a good guess is usually a good place to start. And we don't even need a theorem at this point because there's not much that I mean, it's not too difficult to just come up with this. So let me just go through with this and then maybe later mention the theorem. So why is this a good guess? So for a basis, we need to check two things. We need to verify the first one is independence. And that just means we want to try to find whether a linear combination of P, which is 1 plus x, of Q, which is 1 plus x squared, and the new polynomial, which is 1 minus x, is equal to 0. What does this mean for the coefficients? So we're doing this typical this test for independence. And the way to do this for polynomials is, well, we have to just sort them by the monomials. So everything with the 1 we put in front. So the coefficients with the 1 are alpha plus beta plus gamma. So I'm just picking out these terms that have a 1. And then next I'm going to pick out the terms with an x. And then lastly, it's with an x squared. So with an x, we have, again, alpha, we have beta, and we have minus gamma. And then next, we only have a plus beta x squared. So now, as a next step, we want to try to find we want to make this equal to the 0 polynomial. So remember that this is not just 0, but this is the vector 0 in P2R. So this means this is the 0 polynomial. And this means two polynomials are equal, the 0 polynomial on the left-hand side in this case, and the right-hand side, when the coefficients are 0. So we need to find so we need to solve the system such that alpha plus beta plus gamma is equal to 0. Alpha plus beta minus gamma is equal to 0. And beta is equal to 0. Well, and now we see that either we row reduce this, or we just immediately read off from this. The last line definitely tells us that beta is 0. Well, if beta is 0, then the second line tells us that alpha is equal to gamma. And here we see if beta is 0, we get that alpha is minus gamma. And now immediately we see it's only possible. So alpha and gamma can only be equal and equal to its opposite, to its negative, if also alpha is 0 and gamma is 0. And this means that only the trivial combination is 0. I think my phone is set to to allow it to go back into normal mode at 7 p.m., which is really unfortunate for these lectures. Yes, so only the trivial combination is 0. And this implies that PQR is independent. What else do we need to show? Yes, exactly. Sam said that secondly, we need to show that it spans. So we want that P2 of R is equal to the span of P, Q, and R. Any idea how I could show this? Yes, James.
Well, we can show that we can get 1x and x squared through combinations of those polynomials. And
yes,
then
exactly.
those, we can construct anything.
Yes. Recall there was a previous discussion if we can construct 1x squared from P, Q, and R, then it spans P to R. And there was a certain logic behind this, because we know that P to R is spanned by 1x and x squared. And there was a corollary that I presented, I think last week, in which case two spans are equal. So go back to that if you're confused about this. But this is exactly what we're going to use now. So how do I do this? Well, I have one idea how we can get 1. That's not a problem. Actually, let me create more space. Any? Yes, Benjamin.
To get 1, you could do 1/2 of, I guess that's P, and 1/2 of R, and add them.
Yes, exactly. So we observe, oh, this is too big. We observe that 1 is equal to 1/2 of P of x plus R of x, because this is exactly 1/2 of 1 plus x plus 1 minus x, and then you can see that the x's cancel and we get 1. I guess it's better to write it starting from the left-hand side. But this is what we're trying to do here is the 1. Next, we're trying to get the x. Oliver?
Can we do the same, just do px minus rx?
Yeah, exactly. So the r was very wisely picked, so that we can just do p of x minus r of x. And then we get 1/2 of 1 plus x minus 1 minus x. And because of the minus minus, this time the 1's cancel and the x's come together, and they give us x. Okay, and lastly, what about the Gen C? Do you have an idea?
Q of x minus p of x.
Yes, exactly. That's also very quick. So x squared can be obtained. Oh, no half required. We just have r of x minus p of x, which is plus x squared. And then we subtract 1 plus x and we get x squared. Okay. So just to comment on this theorem that I was hoping we would use, but we didn't. So we could have checked that that PQ is independent. By the extend theorem, part 2, we can add some r of x not in span PQ. This would just be helpful to pick an polynomial r of x if you don't really know where to start. But this might be actually helpful in more complicated cases. So just keep in mind that it might be a good place to attack a problem like this. Someone just wrote me that it might be difficult to read this. Can you read this all right, or is this too small? I thought it was better to keep everything on the page so that when you when I upload this, everything is there together. I mean, you can always zoom into the document, I guess. So it's okay. So any questions before we move on? There's one question, Han1. I don't know if I pronounced your name correctly.
Hi. Why do we, when we're calculating for 1 and x, like at the top right corner, why do we have them? Like, why do we have P?
Oh, because if I did an intermediate step, you would see that this 1 and this 1 would add together to 2. And then to get 1, we have to divide by 2. Same here, you have 2 x's. They add together to 2x. And then you have to divide by 2 to get some x.
Okay, I thought all that matters was we just get a term with x and with 1. Like, it doesn't necessarily have to be like 1.
Not necessarily. Then I mean, we know that 1x and x squared is a basis for P2R. So it's nice to just have back 1x and x squared, but that's just a conventional thing.
Okay, thank you.
All right, so now we come to a very important theorem. And in preparing these lecture slides, I noticed how ubiquitous this thing is going to be in the end, in the remainder of this lecture. So I actually want to take the time to prove this in 5 or 10 minutes. But let me first explain why we care about this. So the important thing is actually a corollary after this, because the basis, as we've seen, there are many bases for the same vector space. So we can't really say that a basis characterizes a vector space. But we still want to have something like a label. So we still want to have something that is typical for a vector space. So we want to talk about something that describes the vector space. And to get this corollary, what we first want to show is this theorem. And it says that if there is a family S that spans a vector space, and suppose this has m elements, then any other linearly independent family in this vector space can't have more than m elements. So basically what this is saying, that as soon as you have a family that spans the vector space, this is an upper bound for the number of independent vectors. That's the idea behind this. Does that make sense? It's you may not really see why this is important, but we'll use this a bunch of times today. Okay, so let's prove this, and we'll just start by giving S the vectors in S some names. So let's say this is V1 to Vm, and R is made up by U1 to UK, and we want to show that K can be bigger than M, as long as this is independent. And this is just so we can also show if K is bigger than M, if K is greater than M, then R has to be dependent. So how do we test for independence? Well, it's always the same. We always try to find whether there's a combination of the vectors in R that equal to 0. And well, let me just pick the beta 1, U1, and so on, beta K, UK. But now notice that by assumption, this spans V. So this means it might not be unique, but for every U, we can actually find, because S spans V, we can find that each UI, I'm just going to stay follow my notation originally because it might get confusing otherwise. So UI is equal to alpha to a certain sum. Let me write this as alpha I1 V1 and so on, all the way up to alpha I M V VM. So notice that this combination, so this is a different combination. For each UI. So the alphas now have two indices. First, to tell us which spot they're in the combination. So if they're the coefficient of V1, V2, and so on to Vm. And this is the upper index. And the lower index tells us which U they are part of. But this is just a matter of going slow and keeping track of what the indices are. All right, now we can substitute this. And let me maybe give this equation here is important. So let me give this the star name. And then what we get is that 0 is equal to beta 1 alpha 1 v1 alpha 1m vm, and this goes up all the way to beta k alpha k1 v1 and this goes up to alpha km vm. So if you compare the yellow equation with this one, then this is just substituting for each UI the expression that we found, that we assume is there. So now we resort this, so we can sort by VJ. So there's many appearances of V1. There's a V1, there's a V1, and there's more V1s in there. So you want to bring all the V1s together. And what happens then is we can observe that this is equal to alpha 1 1. Beta 1 alpha 1 1 plus beta 2 alpha 2 1 and so on, all the way up to beta k alpha k k1 times v1, and this continues until we reach the coefficient of Vm. And now notice again that that the lower index is always the one that agrees with the beta index. So we always have this index, this alpha k with a beta k, and the upper index tells us which V it belongs to. So you can kind of think of this as two labels. And the upper label is always the one that tells us which V this belongs to, and the lower one is for the beta. All right, what was this? I need to finish writing this. So this is going to be beta 1 alpha 1 m to beta k alpha k m. Okay, but now this is we now need that these coefficients vanish. So this means now I guess I need to shrink this a little bit again. No, don't want to take a photo. So now what we do is we just have a condition to sort these in terms of the separate coefficients to vanish. And then from this, we obtain a system of equations. So this is going to be alpha 1 1, alpha 2 1, all the way to alpha k1. And here we get alpha 2 1, alpha 1m, and alpha mk. Beta 1 to beta k. And for this to vanish, we need this system to be equal to the 0 vector. So this means we're looking for coefficients of the last equation that that sets this equal to 0. But now notice that we assume that we want to test the case for k bigger than m. This is what we're looking at. So what is this system? This is a homogeneous system. With k variables and m equations where k is greater or equal than m. No, just strictly greater. So this means there is always, a homogeneous system that can't have any inconsistencies. So there's always has non-trivial solutions. Meaning non-trivial solutions beta 1 to beta k, such that this expression, this combination that we had on top is equal to 0. But this means now that the original equation, so from star, or rather with the equation star, this means that the family R, which contains U1 to UK, is linearly dependent. And so by showing that every family that's greater, that has more elements than S, is dependent, this is equivalent to the assertion of the theorem, which says that any family that's independent can have more than m elements. So that's just identical as the statement. Any questions? Yes, Jagat.
Can you hear me?
Yes, I can hear you.
Can we use this theorem in another way? Like, for example, we know that family of S spans V. So let's say it has n elements which are independent, and n should be less than or equal to m.
I'm not sure what you mean. There might be a different way to prove this.
Like, I mean that family of S has m elements.
Yes.
And we don't know if they are independent or dependent. So I'm saying
Correct.
let's take that n elements are independent, where n should be less than or equal to m.
Yeah, but what do we do if m is some dependent?
Yeah.
If S?
Yeah. So we know that n independent elements span V, and it should be exactly n of them. Like, neither n minus 1 elements nor n plus 1 independent elements will span V exactly. It has to be n, and we know that n is less than m.
I'm not sure I'm following what you're saying. Maybe we can discuss this after the lecture or in a break in between the lectures.
Okay.
But sure, maybe this shorter way. This is actually the way that the book does it too, and I think it's once you read through this a few times, it might make more sense. But for now, if there are, do you guys have questions about the proof, or is this a comment? Oliver.
Yeah, I just have a quick question. How did we conclude that from the matrix multiplication that we get that it will equal to 0 vectors? So what you're saying is that we can get a non-trivial solution from that?
Yes. So notice that the alphas here, the alphas are not up to debate. These alphas they have a certain value because this is how the U vectors are made. So the alphas are not, we can't change the alphas. But what we can change the betas, because those are the parameters that we can adjust to maybe make this equal to 0. So now here, this is in this system, this coefficient matrix is consisting of these alphas. So this is not variable. The betas, however, are the ones that we can vary. And if we are able to solve the system, notice that each line of the system, if you multiply this vector with the first row, this is exactly the first coefficient here. So if we're able to solve the system for some betas where the alphas are fixed, then we're able to find betas such that this whole term is 0, but this is just rewritten of this yellow equation. So this means if we can solve the system, we can find betas such that this is equal to 0. And now we use the fact in the end that k is greater than m, because we were able to basically write these k vectors, u1 to uk, in terms of less vectors, because we know that less vectors are enough to span. So that's maybe the whole reason, which I didn't explain very well in the process, but I'm glad that you asked, because now I think it's clearer that if we're able to write these u1 to uk, which is a long list of vectors, in terms of less f, because m is less than k, of m vectors, then they have to be dependent. That's kind of the how the proof works.
Oh, okay, I see. So because it's less, because m is less, there's a non-trivial solution that will make it.
Yeah, and this comes from 223, which you learned there, that if you have more variables than equations, there are solutions, because homogeneous systems can have inconsistencies.
Yeah, thank you. Awesome, I get it now.
Okay. So I'll be happy to answer questions later, but now I'm kind of getting stressed because it's already late. It's getting late for the time, and there's lots of things we need to cover today. So now that we have this, there's a bunch of things that just follow immediately from this. So let's get this corollary. And because of the time, I'm not going to give you time to think about this first, but I want to immediately just explain the result. So we know that so we know that B, if B is a basis, this means that B spans V. And because B prime is a basis, this implies that B prime is independent. So now we're exactly in the situation where we have one spanning set and one independent set. So this means by the theorem 1,6,10, the number of elements in B prime has to be less than the number of elements in B. This is exactly the case. We have one thing that spans and one that's independent. So we use exactly the two opposite properties of the bases, because in in theory, we know that if they're two bases, they have both properties. They both span and they're both independent. But for this argument, we only need one each. Now, vice versa. B prime spans V as well. And B is independent. And this means by the same theorem, that now the number of elements, and I'm just using this as for a set. This is the number of elements in the set or family, just because it's easy notation. Now, because we just apply the theorem from just now backwards, it means that B prime has to have less, or sorry, equal elements than B. No. Wait. B less than B prime. And together, we know that they have to have the same number of elements. So we just apply this theorem twice and we get this corollary that any two bases of a vector space have to have the same number of elements. Okay, now why is this helpful? Well, we noticed that bases are not unique for vector spaces, but now we have something that even if the basis changes, there's something that doesn't change, which is the number of elements. So this is exactly the grounds for the next definition. We say that, well, if a vector space has a finite basis, this means it has a basis with finitely many elements. We call this this vector space finite dimensional. And secondly, we say that if we are in this case, then the number of elements in this basis, or any basis, which we know is now invariant, is called the dimension of V. So the idea to find the dimension is now very easy. And this is exactly the next discussion. If you find a basis, and it doesn't matter which one of the many choices you have, just count the number of elements in the basis, and then that's the dimension of your space. And yeah, let's take 2 or 3 minutes. You can think about this discussion, and then we'll collect the answers before the break. Oh yes. There's one question in the chat. So last time I mentioned this, I gave symmetric matrices this weird notation S, and I thought it was better to use like more suggestive notation. These are symmetric matrices, and the other one are anti-symmetric matrices. So this is what we previously called S and A. Actually, if you're done with this early, you can also think about the other discussion. But we'll only be able to discuss this the answer to the second discussion after the break, I guess. I've written down here that a matrix is anti-symmetric if it satisfies this property. Yuan?
My cat's meowing. For above, like for when you were trying to prove the corollary. You said that if B is a span, then B prime is independent. How did you conclude that?
Let me try to answer this without moving the slide. I didn't assume that one is independent. I said that one spans. Oh, I did. Sorry, yes. I did say one spans and the other one is independent. Because the basis has to be both. It has to span and be independent.
But why is B prime independent? Because B is a span.
Oh no, it's not because. It's just both true.
Oh, okay.
Because what we assume is that they're both bases.
Mm-hmm.
And then the theorem that we use just says that, well, if something spans the space, then nothing that is independent can have more elements than the space. That's the theorem that we use. Jagat, is your hand still up because of your question?
No, sir, it's from previous one.
Okay, someone's distracting everyone with a cat.
They asked. Sorry.
Okay, we have a few minutes before the first hour ends. Does someone have an idea for the first discussion? Try to focus for 3 more minutes, guys. Okay, Jency is giving all the answers. Let's discuss this one by one. So yes, so the first one is 1. Oliver, do you have any comments?
Yeah, I was just thinking. I was going to say that the dimension of R was 1 because when there's a supposed 1 on the top, so it's like the basis of R is R itself, right?
Well, R isn't independent because it's a set with infinitely many elements. But just the element 1 is a basis.
Oh, because you can make every value in R from 1.
Yes, actually, I think this was a typo. I actually wanted to have Rn here, but never mind. In which case, it would just be more elements. It would just be E1 to En.
Okay.
This is a basis. And now that we just count, there's 1 element in the basis. What about the second one? Yuan, you have your hand up.
No, that was a question. I'm sorry.
Okay, no problem. Someone else about Sam.
Yeah, so the dimension is n+1
Yes.
because like the basis has to, or one basis can be like x to the n plus x to the n minus 1 all the way to like x plus 1. There's like n+1 elements in there.
So did you use the monomials, or which one did you use?
Yeah, the monomials.
Yeah, exactly. That's the, I guess, the easiest basis to consider here. And now the trick is that this has not n elements because there's 1 constant. So we start counting with 0. And so in total, these are n+1 elements in the basis. Okay, matrices of size 2 by 2. Oliver.
I think 2 because it's 2 matrices of a size 2, so that's E1 and E2. Can you just count it?
These are matrices, so remember that a basis of MAT2. What do we have before? I think we talked about this before. So we need something of the shape. We need to span every kind of matrix which is of the size of the form A, B, C, and D.
Oh, yeah. I see now. So it's A matrix like A 0 0 0 and then 0 B 0 0 and then
Yes, correct.
yeah, and so on and so forth.
But instead of having actually A, we can just use 1 because we allow to scale these before we add them together.
Yeah, of course. Okay. Sorry. So
And yes, so the dimension will be 4. Okay, now we get to the interesting ones. I've seen there's been some discussion in the chat. Someone just tell me what's been going on in the chat. I haven't been able to keep up. Adrian.
Yeah, I think for symmetric ones, we kind of agreed on 3 after some teamwork.
Okay. That's good if you agreed and then.
Yeah, so the basic argument went that we would know that a symmetric matrix would have something that would look like A, B, B, D if you just go over it row-wise.
Yes, let me just write this down. So A, if we transpose this, what am I doing here? If you transpose this, then we get this matrix. And if you want this to be equal, this isn't true, but we just want this. We want to make this equal to the original one, which is A, B, C, D. Then I think I explained this before. We want to impose that C and B are equal. So, sorry, what did you say? The general form.
Oh yeah, the general form would just be A, B, B, D.
Yes, exactly.
And then it's basically you get 3 different values which determine like the matrix. So just like because one matrix is going to be 0, B, B 0. The other would be A, all zeros, and the other would be all zeros and D.
Yeah, exactly. So now that we have what the general form is, we can conclude that a basis is, for example, just something that looks like 1 0 0 0 1 1 and this. And then, I mean, this is again, to show that this is a basis is straightforward. We just did similar to calculations that we did before, but you can, so I'm going to skip these now. But then the number, so we have 3 basis elements. And what about the last one? Where should I put this? Let me move this up here. Sam?
Yeah, so I think it's just 1 because the element, I think it's 0, 1, -1, 0 spans the entire like vector space.
Yes. Let me just, let me just write this down. So MAT MAT224, as you said, has to have the form of 0,
yeah,
A minus A and 0. And the reason is if we transpose this, the A and the minus A change places. And so they have to be of opposite sign. And therefore we see that a basis is only, for example, this isn't the only basis. We have 0, 1, -1, 0. Notice that these entries have to be 0 exactly because when we transpose them, they don't move, but they have to be minus itself, and only 0 is the only number that is minus itself. And so this means that the dimension is equal to 1. Okay, any questions before we take a break? Adrian, your hand is up.
I think that was from earlier, sorry.
Okay. I'm going to move this up here. And are there any more questions? No, then let's take 6 minutes of a break, and we'll be back at 2:12. I'll stop the recording until then, if it lets me. So we're live again. This is again being recorded. Any questions before we continue? Anything that was unclear about this? All right, then I'll maybe spend another 20 minutes or so on on this section, and then we'll move to transformations. But if we can get through transformations today, then we'll just resume with this next week. Okay, so this discussion, because at the time I'll just explain you the results and not ask you to solve them yourselves. Okay, so say we have a subspace U inside a vector space V. Then we want to check whether it's true that the dimension of U has to be less or equal than V. That's something that naturally seems true, but we can't just assume this. We have to actually verify this. So let me argue why this should be true. So we can start with the first one. And we just saw that both have a basis. Every vector space has a basis, so we can just pick, we can just say let B sub U, BV, be bases of U and V respectively. Now we know that they're both independent, and BU spans U and BV spans V. But if we now again pick out the thing that we want, namely that in particular, among other things, BU is independent and BV spans V. And notice that the basis of BU has elements which are also in V, because U is a subspace of V. But this means, and now this is the first, the third occurrence of this theorem again, by theorem 1.6.10, we know that BU has less elements than BV. But this is exactly what's equivalent to saying that the dimension of BU is less or equal than the dimension, of U, than the dimension of V, because the number of these bases is exactly what determines the dimension. Any questions? Okay, what about the second one? So now this is also interesting, because if we have a subspace and we know that the dimensions of the subspace and the space are equal, is there maybe some way that we can conclude that the subspace isn't properly contained? So remember that we talked about this in the beginning, that proper inclusion means that it's actually smaller and not the same space. So it can't be, so if U is properly contained in V, then we know that U is not equal to V. Whereas if U is just contained in V, then maybe U is equal to V. It doesn't exclude this case of equality. So now we want to assume that the dimensions are equal and then conclude that that U and V have to be equal. There, it's kind of the contrary to the first point. Let us start again by picking bases for U and V. So again, let BU, BV be bases of U and V. And by assumption, we know that the number of elements in U and in the basis of U is the same as the number of elements in the basis of V. And we want to show that U and V are equal. So let's assume the opposite and show that this can't be happening. So for contradiction, so we want to show if U is not equal to V, so setting up a contradiction, there is a vector V in V such that this V is not equal not in U. And this exists, this vector can be chosen exactly because they're not the same in our assumption now. But this means that BU is a linearly independent family, in particular in V, and V is not in the span of BU. Can someone guess where this is going? This is exactly the setup of the extent theorem. So by the extent theorem, and this is technically the first extent theorem, the first time that we saw this, we can add V to BU to obtain a linearly independent family with, did I give this a name? Let's call this n. Let's call the dimension of both of these n, because I need to just reference this. And we know that BU and BV have both n elements, but now if we add one element and it's still an independent by the assertion of the theorem, we have now an independent family with n plus 1 elements. Does that concern anyone? Is there anything wrong with this? This can't be true. Because by again, theorem 1.6.10, BU has, so no, BV has n elements. And BV spans V. No independent set or family in V and have more than n elements. But we were just able, by the assumption that we made, namely that there's some element in V that isn't in U, to construct a linear independent family with n+1 elements. So that certainly can work. So this means finally there's a contradiction. We just do this symbol for the contradiction, and then for conclusion we can say that, well, this means our assumption, no such V in V, but V not in U can exist. Because if it did, it leads to something that's wrong, and so in the end we know that U and V are equal. And that's it. Yes, sorry, I never know how to pronounce your name. Yan Yuan?
Hi, could you slightly scroll up? Or actually, no, the very first line right now, or want U is equal to V if U is that a proper subset of V, or is that not a subset? Like
let me change this. This sounds confusing. So we want this, period.
Okay.
And then let me start over. If U is properly contained, that's what you asked, right?
Yeah.
Then there's some vector in V that isn't in U, and from this whole machinery getting started up until the point where we have a contradiction. So then we go back and say, well, this assumption that we started with can't be right.
Okay, makes sense. Thank you.
Sure. Any other questions? Okay. This was supposed to be a discussion, but I hope this was still helpful to go through. And maybe actually this would have been very difficult to come up with on the spot. Okay, so this is something that I definitely want to do because this proposition is very useful. So very often we are in the case where we actually know the dimension of a space, but we don't have a basis, or we want to show that something is a basis. And so say, for example, that the polynomials, in the beginning, I was telling you, complete this to a basis. And we already know that the monomials are a basis. And we have actually, in fact, now computed that the dimension of Pn of R is n+1. And if I give you polynomials, it would be to know how many more do we need to add to find a basis. And if you do add these, you might be wondering, well, a basis needs to be both independent and it needs to span. But here, it's actually enough that this proposition says that it is equivalent to have either A, B, or C. So this is a very common way to phrase a proposition. And it means that the first thing here is that what we want. And the second one is enough to show this, to guarantee this. Now, what's special about this proposition? Maybe we should just go through this from top to bottom. So if we have a vector space V, and we know the dimension, that's something that might happen, but it's not always the case. And we also have a family with exactly n vectors. Then it is enough to show that it's either independent or spans the space in order to conclude that it actually is both true. All right, let me go through this proof, but if you have questions, please raise your hand. Okay, so the way that we prove this is actually we assume, because we have to show equality of all of these different points of A, B, and C. So what we can do is, well, we just have to do this step by step. A implies B is clear. By assumption, a basis is independent. Similarly, A immediately implies C for the same reason. A basis is always has to be a spanning set. So these directions are clear. Now what we do need to do is we need to get from B to C. Actually, let me do this the other way around first. So I want to do this direction first. So I want to show that if we have C, we can actually imply B. So now suppose S spans V, but S is linearly dependent. By the reduced theorem, we can remove an element and this is exactly because it is a dependent family. This is the grounds on which I'm able to apply the reduced theorem, such that the span of S is still V. Actually, let me change this here a little bit. Let me say that we can remove one or more more elements, such that this still spans V, but eventually, but S prime now and S prime is independent. But this would mean that now the new S prime that we have removed elements from in order to, like from S, but the number of elements, so the number of elements in S prime is strictly less than n, because we removed some elements. But this would mean that the dimension of V is equal to is less than n, which isn't true, which violates dimension v is equal to n. Sorry, this proof doesn't really make sense. What am I saying? No, sorry, it does make sense. I was just confused because the fact that we assume the dimension of v is n is in the beginning, and it is not part of a, b, or c. Any questions? I'm sorry, this was a bit confusing, I think, but it does work. Now let me skip the last part. You would technically also have to show b is some sorry, I didn't finish this. So now, because we did assume that is dependent to derive at this contradiction, this means that S is actually independent. And this is exactly what B is about. So we have successfully arrived at B from assuming C. So now, and then also, this also says that C applies A, because if we start with independence or with span and arrive at independence, then we also arrive at basis. So these two go together. Now left to do, and I'll leave this for you as an exercise, to show that B implies C. Oliver, you have a question.
I'm just unsure as to why all of a sudden you use span of S prime and like used S prime. Like, where did it come from?
Oh, so when we apply the reduced theorem, what it tells us is that if you have a linearly dependent family that does span a space V, then we remove elements until it is independent, but we don't change the span. And so S prime, S prime is, let me just write this here. S prime is S minus some elements.
Okay, from the reduced theorem. Okay.
Yes, exactly. And then we are able to conclude that there's a problem, because if we remove elements, then we have less than n elements in S prime, but it is independent, and now it still spans V. So we have a basis with less than n elements, but we in the beginning assumed that the dimension is V. So therefore there's a problem. Yes, Mallory.
Hi, I was just wondering, have we proven, or do we need to prove that B implies A? Is that something that we already?
Yes, yes, this would be part of the homework. So, well, not necessarily homework, but I don't want to do this right now because it's a very similar idea. It follows from this last step that if B implies C, B and C together imply A.
Okay, thanks.
All right, let me just check what else is on the agenda today. So we could do this discussion. I kind of want to skip these discussions. Okay, I think I want to spend 10 minutes or so on this section still. So let's do this discussion, and I'll give you 2 minutes to think about this, and then we'll just collect ideas. Oliver, can you type your message in the chat? Then I'll read it and answer it in the chat.
No, it was just from before, sorry.
Okay. And as a hint, I mean, it's in the same space as a proposition we just proved. So this is something that you might find helpful. Okay, let's collect the ideas that you have. How would you approach this problem? Yes, can you be more specific, Oliver? I mean, how do we apply the theorem above? We need to have certain things to be able to apply this. So we need to have a vector space of a certain dimension and a family in it containing the same number of vectors. Yes, Andrew said that we can verify as a first step that it's independent. So I'm not gonna waste time writing down any sentences, but I guess by now, if you see something, an equation like this, your brain should always fire and say, well, this is what we do to test independence. So what happens if we try to find a combination like this that is equal to 0? We just reorder this. We sort this by monomials. 2 alpha plus beta x, and then we have minus alpha plus beta x squared. Well, and you see, if you want to make alpha plus beta equal to 0 and alpha minus beta equal to 0, or rather, it's minus alpha plus beta only if alpha equals beta equals 0. So we know that they're independent. Okay. So yeah, we could show that they span the subspace, but the point here is that we want to do this in a way that uses the theorem of the proposition above. So now the next step is to find what is the dimension of the subspace. Yes, Kevin, that's right. How do you know that it's 2? Yes, correct. This is a plane. So this is, let me write this in the way that I would formulate this. But what Andrew and Kevin wrote in the chat is absolutely correct. So this is the solution space to a system of well, system of one equation in 3 variables. So this means that the dimension, and then this is also homogeneous, so you know that there's no inconsistency, but this means that the dimension is equal to 2. This follows from something that you had last semester in linear algebra 223. So now this is all we need to check. We don't need to check whether they actually span the space. Well, we need to check that they're actually in there. That's a good point. So 1 plus 2x minus x squared and 1 plus x squared. They're both in W. And now, I mean, I noticed that this is not maybe the straightforward thing to do it, but I want to just force this way of proving it, because there might be situations where this is the only way, and now we need to practice this in order to apply it in the case where this is the only chance we have. Okay, so now by the proposition above, this is enough to conclude that, I didn't give this a name, S is a basis of W, because it has 2 elements, and the dimension of W is 2, and it's independent. So the fact that it spans W comes for free. Any questions? Oh, so family and set is technically the same. I just want to emphasize when we say family of vectors, that this is something we want to make into a basis, so that we want to check independence of. A set, I mean, a set is something that we were talking in the beginning, that we eventually need to upgrade to a subspace. So a family, even though it is not defined in any way, is usually by convention something that doesn't have infinitely many elements. It's just finite. Well, that's exactly, I mean, Kevin just asked how we show that it spans W. Well, you'd have to find the most general way to write an element in W and then show that you can obtain this from linear combination of the elements in S. But to avoid this, we can use this proposition. The dimension is 2 because it is the solution space to a system of one equation with 3 variables. So remember that that the rank, or not the rank, but yeah, it is. There's the number of parameters in the solution space is always this n minus k or something, n minus r. So here is the system of equations that cuts out any vector that solves this the system gives us an element in W. Yes, 3 minus 1, exactly, in this case. All right, so there are more discussions and another example, but I would like to skip this right now. And the only thing I want to show you is this theorem without proof. This is part of the book, and this is theorem 1618. And it says that if you have two vector spaces, or two subspaces in a vector space, then they might have an intersection. I mean, for example, let me just draw something. If you have the XY plane, and you also have the YZ plane in R3, then you can notice that the dimension of this is 2. The dimension of this is also 2, but the dimension of the ambient space in which they both are embedded is 3. So the question beforehand, the discussion would have like asked you, is that possible that the sum of these subspaces is that the dimension of the sum of the dimensions this way is bigger than the dimension of total space around? And it is indeed possible. And the difference between these two numbers, so if you add together the dimension of the subspace and you compare this to the dimension of the ambient space, then there might be discrepancy. And this discrepancy is exactly the dimension of the intersection. So here you can notice that there is the y-axis. It's a little bit off, but so this is the y-axis, which is both in the YZ plane and the XY plane. This is a line which has dimension 1. So basically, I'm just explaining this theorem with a picture to help you get an intuitive idea for this. But it means that whenever you have two subspaces and they intersect, then you shouldn't count. And if you want to add these subspaces together, so in the left-hand side, you see, if you add these subspaces together, well, if you add these two planes in the picture, you do get all of R3, but this Y plane is twice in the sum, so it's kind of a redundancy. And so this theorem tells us that this is the general correlation between the sum of the subspaces and the dimension of the subspaces individually. Yes, so I don't know how to write this right now here, but let me give these names. So if U is the YZ plane and V, I use U and W. Then in this case, in this example, U plus W is all of R3. And you can show this. You have to show that every vector in R3 can be written as a sum of a vector lying in the YZ plane and the XY plane. We've talked about this in a previous lecture. I'm pretty sure that we've had this. Okay, so let me use the last 10-ish minutes to move to the new section. There's more discussions here. They're very similar to what we've done before. So if you want to have more material, as I already announced at the beginning of yesterday, you're welcome to look through this, but don't feel overwhelmed. This is it doesn't mean that we're missing out on content. And maybe if we have more time in office hours or next week, we might just go back and do this again and do this some other time. But feel free to look at this yourself, and if you have questions, then let me know. Okay, so now it's time to add another ingredient to our discussions. And this is very important because so far we've talked about spaces, subspaces, but there are functions between them. and they play a very important role in understanding linear algebra. So whenever we have a function between two vector spaces, this is just a function same as the function between sets. But in this case, we want to distinguish a few of these functions, namely if they behave nicely with the operations that we defined. Remember that there's what makes vector spaces to vector spaces is that the sets have an additional addition and multiplication. So now a function is called a linear transformation, or just linear, and we'll later call them linear transformations, if the transformation applied to the sum of two objects is the sum of the objects with the transformation applied. So on the left-hand side, we apply the plus first, and then we apply t. And here we apply t first, and then we apply the plus. So it's like the order matters, or in this case, it doesn't matter which one you do first. Likewise, for the multiplication, if you apply t to a scalar product of alpha times u, it's the same as first applying t to v and then applying alpha, then multiplying with alpha afterwards. So the domain and the target of a vector space of a transformation have to be vector spaces. It only makes sense to talk about linear transformations when we have a function between vector spaces. So this definition itself doesn't tell us much. I guess we just need to be look at examples, and I just noticed that I didn't put any examples here. So I guess we'll just go to the next page where we have a discussion. I guess I meant to delete this, so we have already plenty of examples on the next page. Just let me make two remarks. Well, the first one is we could just call them transformations when they're linear, but we really mean linear transformations. And one important thing is I was very pedantic here, distinguishing the plus operation on V and the plus operation on W. So I gave the pluses a sub-index, a label. The reason is because if you have two vectors, say you have U and V, and they are in V, then it makes sense to add them together. But you can only use the operation defined on V. Once you apply T, because T is a transformation from U to V, W, V to W, then T of U and T of V are no longer elements in V. They've now become elements in W. So now if you want to add these together, it doesn't even make sense to use the operation in the domain. You have to use the operation that's provided in the space you're in. So to use the same operation here and here, were to say you have vectors in one space and use the operation of another space, which, if you're not careful, you might just overlook the fact that this isn't even possible. So please do me the favor and don't confuse these two things, because sometimes they are the same, but sometimes they might actually be very different. Actually, yeah, I just thought of an example which might be helpful. So let's actually look at an example. Say we have the real numbers, and we have plus and multiplication, just the standard real numbers. But now let's say that there's a map that maps to the real numbers, and we remove 0. So this is R. This is R without 0. So now you might wonder, is this still a vector space? And it certainly is indeed a vector space if we if we define the sum as multiplication, so in this case r, let me define this plus tilde plus, then we can say that r that a tilde plus b is equal to a times b. And in this case, we might have we might have a transformation. We can define the transformation. I'll leave out for now what the multiplication is. There's a multiplication that goes along with this. We might have a transformation t such that t of r is equal to e to the r. So r is a real number. And notice that e to the r is actually never 0. So it makes sense to have a transformation from the real numbers to the real numbers without the 0. And here, for example, what is the identity? Is 1, because if you have a tilde plus 1, which is secretly a times 1, this is a, which is exactly what the identity should be. But this actually was just to show you that that you should be very careful with the operations in transformations. Okay, but now this wouldn't be an example of a linear transformation if we didn't check that this was actually linear. So let's check, is this linear? Well, kind of running out of space here. So linear means that t of r plus say s has to be equal to t of r plus t of s, but not just plus. When I say plus after applying t, I mean the tilde plus. So now let's just compute this. This is e to the r plus s. Well, luckily we have this property that this is equal to e to the r times e to the s, and this is equal to t of r tilde s tilde plus t of s. I'm gonna have to resort this whole thing. This is a mess. I'm gonna clean this up after the lecture, but let's just continue for now and pretend this there's nothing written there. So what we also need to check is that that c, or did I think I used alpha? Yes, I used alpha. Alpha times t of r has to be equal to no, I wanted to apply this first. So if I start from the left-hand side, I have alpha multiplied with r first. And then I need to bring this alpha in front of the t. So what is this? By definition, I've said that t just takes a number and exponentiates it. So it takes it to e to the alpha times r. Well, now what we see is that we can write this. Well, now I guess I need to define what. Let me now define here what the other operation is. So I want that alpha tilde scalar multiplication times, I guess, a is equal to e to the alpha times a. So the tilde multiplication is defined by first exponentiating the alpha and then multiplying the a with the usual multiplication. And now we see that, does this work out? Oh, no, sorry. I obviously didn't prepare this example, but it does work out. If we do alpha a to the power of alpha, now you can see that this makes sense now, because now we can rewrite this as e to the r to the alpha. Well, e to the r is just t applied to r. I have no idea why I always write at an angle. This is kind of driving me crazy. Okay, I corrected this. So now e to the r is just t applied to r. But exponentiated by alpha is nothing else than the scalar multiplication defined in the target space. So this is just alpha tilde multiplied with t of r. And now the upshot, and this is probably what I should end with. If you look at the left-hand side, this is all, t applied to a scalar multiplication, and the right-hand side is a scalar multiplication applied to t of r, and likewise on this line, again at an angle. What we see is on the left-hand side, we started with this expression where we have a sum inside the argument of t, and we've been able to bring this to switch the order of applying the addition and t. And this is true for any kind of vector in R and scalar in R. So now by these two computations on the bottom, we see that these are exactly the conditions we want to satisfy for linear transformation. And this means that t is linear. Okay, this was just a quick first example. I mean, maybe not so quick, but this is just one example which emphasizes that the operations are not necessarily the same. And next week, we'll continue this, and then we'll see more examples. So if you're curious, there are more examples. Some of them are transformations, some of them are not. And we'll continue looking at transformations next week. You're free to go now. But I'll just stick around for a few minutes if there are any questions. Yes, Yuan asked for this left-hand side here. Where is it here? I'm using the standard addition because this was what addition was defined to be in the vector space. Yeah, and the question goes on because with an answer, because exactly we haven't applied t to R and S yet, so R and S still live in the domain, and in the domain the addition is just plus. I really hope that spending this much time on this this detail helped you to remember this for the rest of your lives, so that we'll never make this mistake. Any other questions?
Professor, can I ask a question?
Yes.
It's from the previous one that we have one equation and we use 3 minus 1 and we get 2, that question.
Yeah.
So is it because that P2 actually has dimensions 3, but we already have one equation, so we just 3 minus 1. we got 2.
I think I didn't explain this. Like I should have said that I should have mentioned something else, namely that the rank of the system, solution space to a system of one equation in 3 variables. I should add here one thing. 1 second. Of rank equals 1. So you can see that this is the coefficient matrix would be -3, 2, and 1.
Yeah.
So we see that the rank is maximal, which is in this case 1. And then you
because
have this
we
property
find
that, sorry, what?
So because we only have 1 equation, the rank is 1.
Yeah, if if you reduce a matrix to RREF,
Yeah.
then the rank is the number of leading ones.
Oh,
And if you have just one, if you just have just one row in a matrix, which is not all 0, then the best you can do is you will always have a leading one.
Oh, okay, yeah. So that one is related to the matrix, actually.
Yeah, and then you have this number of parameters is equal to number of variables minus rank, which usually is n minus r. This is like one of the first theorems that you learn in linear algebra 223.
So like rank nullity theorem?
It is related, but this is not the context in which you learn this usually.
Okay. Yeah, I got it. Thank you.
Okay, sure. Any other questions?
Oh, hi, Prof. Can I ask a question about in page 2 of the whole slide?
Oh, yeah. 1 second. Yes.
Yeah, I'm wondering that for the remarks, the first one will maybe not this page.
Is this not?
No.
Do you mean page 2 from today?
For the whole week 3 document.
That would be here. This is page 2.
Yeah.
But there's no remark.
Oh wait, maybe the page is different, I think.
This one?
Yeah. Yes, this one. This page, yes.
Yeah.
Maybe it's on page 2. Okay. I'm wondering that can infinite span set like the polynomial R have a basis?
Well, you can define something like this. But for this course, we don't really need this. So we're not going to bother working with this.
Oh, so we are only dealing with finite span sets with clear basis.
Yeah, because at the end, notice that we define dimension. And then the reason that we defined dimension was because we have all these interesting theorems of like this discussion. Where was it? We had, like this theorem, this doesn't even make sense if one of those spaces is infinite dimensional. Because what's the difference between, what's the intersection of 2 infinite dimensional vector spaces? If it's infinite, then there's like, it's all infinite. So there's no interesting relation that we are concerned about.
Yes, I see.
It still, I mean, I'm not saying that infinite dimensional vector spaces are useless. And they do appear in math. But at this point, we're so new to the material that we just need to establish the basics, and the basics are best observed in the finite dimensional case.
Oh, I see. So we will not discuss about infinite basis like that. So
yes,
because we are
exactly
looking at some relationship between finite span sets. I got it. Thanks.
You're welcome. Okay, if there are no more questions, then I'll just end the lecture here and clean up this mess. I guess I have to squeeze this into the space there somehow. And then we'll just resume here next week. I'll also remind everyone that these slides are available on my GitHub page. I was afraid to tell you because they're in very rough state at the beginning, but it might be helpful if you have access to them on the fly when I update them. Okay, see you next week, guys.